So let's get this thing started. I'm going to present you the hidden multivariate patterns method, and this is basically a way to analyze your EEG data, but at the trial-by-trial basis. And I'm going to start by showing you what is actually the problem with event-related potentials. Usually what you do is that you record EEG from the scalp of a participant who is performing an experiment, and this experiment has several trials. For example, a trial would be defined as the onset of a stimulus. In this case, what you have is that you have there's such kind of traces, right? By trial, you have, for example, if you take this electrode around here, you would have this kind of time courses, right? It shows that you have some microvolt values and it's noisy, but you do see that there are a bit of a pattern. Actually, this one is simulated. Usually you would even see less than that. But the idea of event-related potentials is really that if we just average all those trials together, right? If we just get rid of the dimension trial and just average that particular electrode, what we get is something like this. This is a plot from Wikipedia. If you look at event-related potentials on Wikipedia, you would see this one. And what we usually do and what we expect is that when we average things, then noise cancels out. And the only thing that remains are actual brain potentials, right? That are related to the onset of the stimulus. And thus also with the idea that this is related to the task that participants are performing, right? If you would have a detection task where you have to press a button as soon as you see a stimulus, then you would see something like this. Or if you have some kind of decision-making task, you would also see something like this. But this is very old. This has been around for already since the 50s, even earlier, when it comes to event-related potentials. But the thing is that also since that time, we know that those objects aren't really easy to interpret. I'm going to show you how dramatic it actually can be using some simulated data. So first, two important facts. The first one is we don't know the single trial ERP generators, right? When you look at the single trial, you see something that is noisy, and you don't actually know what exactly the shape is of the component that you're interested in. There are two classical theories. The first one says that if enough neurons fire at the same time, then you would see something on the scalp. That's called the classical theory. Then there is this phase synchronization theory, where the idea is that when you do something about the information you're receiving from the stimulus, then you have a lot of neurons that sync in phase. And the fact that they sync in phase makes that they all discharge at the same phase, and thus that you can then see an activation at the scalp level. In both cases, these theories kind of suggest that what you expect at the single trial level is some kind of peak during the single trial time course of that particular electrode. That's the first fact. And the second fact is that brain potential vary a lot in time. We have been knowing that for very long, but we might have misrepresented ourselves how bad this can be. So this is an example of a paper by Lee and collaborators. So that they went intracranial and they looked at the onset of neurons in V1. So V1 would be the earliest visual cortex that you can record. And what they observe is that it can go from anywhere between 20 milliseconds and 120 milliseconds, right? With a certain probability of appearance. But still, even when you look at the lowest level in terms of cortex of where the information arrives, the variation in time is dramatic, right? So this is already pretty bad news, because when you go and look at an ERP and you look at something that happens at 100 milliseconds, maybe that the underlying truth is actually that this thing is happening between 20 and 120 milliseconds, right? So this is already some kind of time jitter and will have a consequence on how we analyze our ERP data. So I made a simulation here, very basic. I just assumed some kind of distribution based on their paper. And what I did is that these are simulated trials. There is no noise at all, right? It's just that at the given time, a simulator has sign, depending on the sampling that I did for that trial, right? So this is the distribution. And this first trial, well, the point that I sampled is 100 milliseconds. So I added this half sign, the peak of this half sign, at 100 milliseconds. And then you see that you can have different timing based on the sampling from this time distribution. So, okay, maybe it's not too bad. But what we can do already with this very simple example is take a look at the average ERP that you will obtain if you have this noiseless data, where the only thing that happens is that you are jittering in time. Well, this would be the representation. And I don't know how shocked you are. Maybe you are not shocked at all. But the thing is that this is the average representation. There are two things to see. So each of those lines is a single trial, and this big line is the average peak time. And what you see is that first, the value of the potential, which is completely arbitrary here because it's simulated, is much lower in the average ERP than the single trial, where it's more like 100 microvolt. This is because we are averaging things. In some cases, the peak is there. In some cases, it's not there. So it's brought down by this averaging process. But I would say, in my case, especially because I'm working on mental chronometry, the worst part is that the peak of this average ERP is not even the average peak at the single trial level, right? So if we say that something based on the average ERP happens at 100 milliseconds, that actually might not be true at the single trial level. This is not new. This is known since at least the paper in the 70s, and if not before, because when we average these curves, and if the variation is also not symmetric and is high in this case, then you would have such kind of phenomenon. This is not surprising, and this is not something new, but it's something we might tend to forget. Now, okay, this might not be that bad yet because we are still close to the stimulus. So the time is actually not that bad. But imagine if I take exactly the same distribution, so this blue histogram, but instead of having only one event, I add another event that is sequential to this blue event. So let's imagine this. I have again the same distribution, but both are dependent, meaning that the first blue one has to happen before the orange one, sorry. And then this makes that the time distribution, even though it has exactly the same properties as the first one, is already much further and much broader than the first one. And we can take a look. That's a single trial representation. And again, what we see is that the peak is not really aligned with the average peak, that the potential is even lower because we are kind of confounding two opposing half signs. But okay, that's still not that bad. Let's imagine that I have a third event that depends on the appearance of those two, right? So the time of the third event will depend on its own distribution and on when the yellow one, the orange one happened. And that's this green event. And you see that the variability in time basically increases as you go further away from the stimulus. This translates into an even lower peak, again, because it's partly being canceled out by the previous one, but also because, as you see, it kind of starts to really stretch out in time because this green event can happen between 50 milliseconds and 350 milliseconds. So it's starting to look quite bad, and we are only on the average ERP, we are only below 200 milliseconds, right? So we're not even that far away from the stimulus. Let's just imagine that we add another one, so this red one, that has exactly the same distribution as the blue one again, but it's just that it's dependent on the other. So in that case, also, the time variation becomes even more dramatic. And what is funny to see is that you don't even see that there are two peaks here on the average ERP, right? So when you kind of read your ERPs as this is this component, this is this component, and there are three of them here, well, this is actually wrong. So maybe this is not the most convincing. It was mostly educational. It's the idea of showing that here. So what I did was to take again this ERP from Wikipedia, and I've been playing around a bit to reproduce the same one based only on simulations. So you can see it's quite close, right? We have a P1 wave, N1 wave, P2. So usually we just give the sign and the order of appearance. And sometimes you would hear also N200 or P300, but the principle is the same. So we would look at that average ERP and say, well, there's a P1, N1, P2, N2, and P3, or P300 if you prefer. But the thing is that here, I actually know how I generated this. And I'm starting to smile because I'm just thinking about what is behind. And what you see, what I did at the trial level was this. So I would just, again, have these time distributions that are exactly the same, but just sequential to one another. So you have this progressive decrease in the sharpness of the distribution. And I also varied the amplitude of the components. Now, the first thing you can notice is that there are actually 7 components, while I only read 5 here or here. And you see that the bi-trial representation is very, very different from this curve, right? No single trial looks like this one. Why? Because this is coming from an averaging process, right? So you're basically looking at something that doesn't exist at a single trial level, which is super annoying. And this is another thing that we can plot. Again, you remember that I showed in the previous figure that we had this average peak time, and we can look at how the average peak on the ERP actually captures the average peak at the single trial level. And this is the reality, right? So each bar is the average peak time of one component. And I didn't even do it on purpose, but you can see that none of the peak from the ERP actually aligns with any of those average peaks, right? So if you wanted to say something about this, the latency of this peak, this wouldn't be representing either the brown one or the pink one or even the purple one, right? So this is very dramatic because usually what you would do is just have two conditions and look at the peak of the P300 and say, well, there is a decrease in amplitude of this component, showing that this is related to whatever cognitive process. But you cannot be sure of that because it could be a time difference. It could be a question of number of components. It could be a question of amplitude indeed. But you have no way to argue based on the average ERP alone what the effect of your condition was on the actual brain potential that are captured by the average ERP. Right? So this is pretty bad. We have been knowing that for a very long time. Again, this is nothing new, but we kind of tend to forget. And when we see a difference, we're like, oh, well, at the 200 milliseconds, there's a difference in amplitude showing that and that. The truth is that you cannot say that, right? So when you write a paper, when you write an analysis, you always have to keep that in mind that you cannot infer from the average ERP alone what is going on. There are some methods to deal with that. I also recommend the book by Stephen Luck on an introduction to event-related potential, where he introduced some measures that kind of alleviate a bit the problem. But what I'm going to show you today is a bit different, and it's a way to model the EEG starting from the trial level, as we do here, but of course not with the simulated data, but with real data. So that's the hidden divide pattern method, and I'm going to show you quickly how that came from, and then we're going to go into the core details of the method. So far, everything going good?
Yes.
Great, thank you. So HMP or hidden multivariate pattern method comes from the hidden semi-Markov model multivariate pattern analysis. It's a very long name. That's a paper by John Anderson and colleagues in 2016. So they applied it to EEG, but also to MRI before. And the idea was, so I don't know if you're familiar with John Anderson, but John Anderson is a creator of ACT-R, which is a cognitive model where you have different operations that can be used by participants to solve a task, right? So it's a theoretical cognitive model. But they have these different steps in the way they resolve a task and with the participants resolve a task. So they basically built this model for EEG and MRI based on this same idea that participants are progressing across different information processing stages, and that these stages must have some realization in the EEG or the MRI that we can then observe. So they built a very nice theory around that and a model around that, and we basically just started from where they left off to try to make this idea and this modeling even broader in terms of use in experimental settings. And that's how we started with hidden multivariate pattern model. That's worked with it with Jelmer Borst and Leendert van Maanen in the Netherlands. And the idea is as follows. This is first a very shallow introduction, and then we go deeper into the detail. But the idea, the fundamental idea of an HMP model is that you have an interval, a duration, that contains a given sequence of brain potentials. And in this case, we assume that those are topographies represented at the scalp, right? So something that you would record at the EEG. But the idea is that between the onset of stimulus and between, for example, the response of a participant, but you can think of anything else like saccade or producing a movement or whatever, the idea is that in this interval, the recorded EEG that you see here simulated contains those topographies, but of course, the noise makes it impossible to see it at the single trial level. So what HMP does is that it tries to resolve and estimating parameters, both regarding the space, meaning the topography of each of those events, and the time. That's why we call channel parameters and time parameters. But the idea is that if we know how the events are represented in the electrode space, and if we know when it likely happens in that interval, then we can reconstruct an estimation of where things happened in time at the trial level. So that's quite a strong claim and a hard goal. So I'm going to show you what are the assumptions, how the method works, and therefore also to allow you to have a better understanding of what this method can do and what it can do. So the first step is a cross correlation. I'm not sure whether you're all familiar with that, but this is actually quite easy. And for the rest of this HMP method section, I'm going to show you always a plot on the left side and the equation on the right side. If, as me, you prefer comic books to books, you can just look on the left. And if you really want to know the math behind, you can always look at the right and come back to those slides that is shared on the GitHub. So for this first step, the idea, and the one also, again, a fundamental idea of HMP is that we have a pattern in the data. So the topographies I showed you are expected to be represented in the EEG data by a specific activation function, if you want. Like this would be, in this case, a half sine. So you just imagine a full sine wave, but you just cut it at half. And this would then be some kind of bump or like pulse activity. And it has a certain duration. In this case, it's 50 milliseconds, right? So we, in this case, in this specific implementation, in this specific, initiation, we expect that this pattern would be 50 milliseconds in the data. We can discuss later about how to relax that assumption and what the consequence is of having the wrong assumption, for example, in this case. But so the first thing we do is that we take, in our case, I showed you 4 simulated channels, blue, red, orange, and purple. And what we do is that we basically take this pattern and we slide it through the actual EEG trial that I have displayed here. That's why you see something that is of lower frequency than the initial data, right? Because we have basically filtered using this pattern to show at the trial level, for each electrode, how much did it look like this, basically, right? That's what the equation does. It's just computing how this sample and the 5 next samples, for example, are looking like this pattern. And you do that for every sample up to the end of your duration, which in this case would be the moment of the reaction time or the response. And you do that for every channel. So for every channel, you have a time series here that is telling you how much does the electrode look like this pattern. So once you have done this cross correlation, this first step, then what we do is very similar to most of multivariate pattern application that you can see, whether it's an MRI, MEG, EEG, or else, is that we have a certain representation of this of the event. So let's for now focus on the first column here and on the first yellow line here. So the idea of multivariate pattern analysis is that a certain pattern, so for example, this half sine, is not represented only by a single electrode, but instead is generated by a combination of electrodes or of, I don't know what, voxels or anything, right? This is, again, very, very standard MVPA analysis. So if I decompose that, the colors represent the coefficients of the channels, and on the y-axis you have the channels. So channel 1, 2, 3, 4, whatever those are, it's just to illustrate. And this would then be the first event. So what this first column tells us, let's imagine that 1, 2, 3, 4 is from anterior to posterior. So all the central channels, for example, if you had only 4 of those. And what this basically tells us is that we have, for the first event, a frontal negativity, if we assume that those two are more frontally placed, and the posterior negativity. Let's just imagine that situation. So this tells me that the pattern I'm expecting is this half sine that is distributed among the electrodes according to this gradient, according to these coefficients. So what I do now, from the plot I showed you here for these 4 electrodes, is that I basically, for each sample, take the value of those 4 electrodes, multiply that with the coefficient that are associated with each channel, and sum that together. And this then gives me one sample here. And I do that for all the samples in the trial in the time series. So for each of this multivariate pattern event, I do that, meaning that I first apply this mixing matrix to the actual channel data. And then I get this, which is basically the linear combination of channels, and which shows me, again, how much does the data, so the real data, the cross-correlated data, agree with this particular mix. So if we look at the yellow curve, we see that this particular mix of electrodes, frontal positive, anterior negative, is happening. We have a lot of evidence to say that it's happening at 50 milliseconds, and a bit of evidence to say that it's happening at 350. And we do the same for the second event, except that the mix is different, and for the third event. So for this part of the talk, I'm just assuming that there are 3 events in the data, and we'll see later how we actually estimate that from the data. But so this is a representation of the second event. This case is a bit opposite, like we have frontal negative, posterior positive. It's not exactly opposite, it's a bit different. And we see this multivariate pattern that is appearing between 100 and 200, and a bit of evidence again that's happening around here. And if we look at the last one, then we see that this matrix, so this vector, sorry, resembles a lot the first one. And that's why when we see evidence for the first one, like this yellow one, we also see evidence for the blue one, right? So there is some shared information between those two, and that's basically what I'm saying, that just to illustrate how the method works afterwards. But if you would do a multivariate pattern analysis, a classical one, usually you would only have one of those vector, and you will only have one of those curve, and just analyze the data by looking at where did something in the data look like this specific multivariate representation of this half sign pattern. So now what goes next? Because for now I didn't describe anything new. Well, the very interesting part that Anderson and colleague added was that we expect that these events that are between stimulus and reaction time are sequential to one another, right? And this also resembles what we know a bit about the brain, meaning that if you go to visual area V4, it's because you have first been through V1, right? So you have this idea of hierarchy that is sequential also in this case. So how do we do that? Well, we start again with this multivariate pattern time course that we saw before. Really, it's exactly the same, except that I removed the other ones, because it's simpler to explain when we only have one. And on the next slide, I'm going to show you how it goes a bit crazy when we have several ones. But when we have only one event, it's really to make you understand how this is working. And this is actually straightforward. I wouldn't say simple necessarily, because it depends on your background. But what we take is that we take this linear combination, so this multivariate time course. Remember, we went through convolution to the electrodes. Then we had, again, this mixing matrix that gives us a one-dimension vector, and that shows us how does the data look, this original 4 electrode data look like this multivariate pattern. And what we do is that we assume a given time distribution. That's this red term here. So in this case, we just take a gamma distribution with a shape of 2. We don't care about the exact specification, right? It's just to say that we have some expectation on when this thing will happen in time, right? X-axis is always time. In this case, what this distribution is saying is a bit in the Bayesian prior way, that I expect that this first event, this first multivariate pattern, will happen around 70 milliseconds, but definitely before 300 milliseconds, right? So it's a bit acting like a prior into shrinking where this multivariate pattern can actually happen. And what we do here, although it looks a bit long, it's actually just to take this linear combination at a given time t and multiply that, take the product with the time distribution. So this makes that every of those points will be weighted by this time distribution. That is the one that when we expect things to happen, this first event. And if you do mentally the operation, what you should end up with is this representation. And you can see that it's a bit different from this multivariate time course, especially on the later part, right? Because we have imposed this time distribution, and because this time distribution doesn't allow actually things to happen after 300 milliseconds, then the evidence we had for a multivariate pattern completely disappears on the later stage of the trial, right? So this can be seen as a way to increase signal-to-noise ratio also in EEG, but of course it also has its downside, right? Because we have the strong assumption that nothing is happening here. So just this is estimated, as we're going to see in a few slides. But in this case, this would happen this way, and in other data sets, it would happen another way. So now what happens when we add an event? So when we are estimating more than one multivariate pattern event, well, then we need to account for the previous one because we are assuming that they are sequential. And that's where things get a bit more complicated, right? So we still have those multivariate pattern representations. We, again, have one distribution that I choose to be that long for this green event. So we expect that this green event will happen, again, before 400 milliseconds, but with more probability mass after 100 milliseconds than the previous one. So we expect this one to be a bit longer. But what is subtle here is that we expect that this will be sequential. The green one will be sequential to the yellow event. So this is actually not representing from stimulus, but from the previous event. So what we're saying here is that whenever this one happens, Like imagine I would only have a single value at, I don't know, plus infinity. Then this would say, okay, starting from here, I can have this distribution. But usually we don't have a single line here, right? We have a distribution. In this case, what we need to take into account is the convolution. And that's where we require a bit more what we call dynamical programming by using forward-backward algorithm. It's not really necessary that you really understand the method behind that, but you only need to understand the intuition, right? If I take this forward variable, this is a backward variable, again, it's just to estimate probabilities, but the really core idea is contained here in this part of the slide. If you have the first event, as I told you, we just basically take the time that we multiply with the multivariate time course, and which gives you this new representation. However, if you take into account, if you're now looking at the probabilities for the second event, then you need to take into account the forward probabilities or the backward probabilities of the previous event. And that's the whole trick about it. So we basically take this line here that we convolve with the time distribution in green. And we take the product of this convolution with the actual multivariate representation, right? So what we end up with is something with both three terms, the time of the event, taking into account the time of the moment of the previous event, and also the actual evidence that we have in the data for this particular multivariate representation. And if you compute that for all the events, then you can compute a likelihood and also a probability distribution, like the one we're representing here. And if we add the third event, the logic is again the same. We use this multivariate representation with this time distribution, but this time we convolve the time distribution of the blue event with the probabilities of the second event, because it already contains the one of the previous one, and with the actual multivariate time courses. And that's why you see that in the multivariate pattern time course, we had evidence for this event at the beginning and at the end. But given that we took this convolution with the previous one, and because the blue one always happened after the yellow and the green one, then there is no probability at all that it happened at the beginning of the trial, right? You can imagine this a bit as this is a sensory event, this is a response event. If you have a response, it's because you had sensory event, and then you're basically just implementing that assumptions in the estimation you do of your multivariate pattern analysis, right? So it's really just taking time into account. So this was presented previously as a hidden summary Markov model, but it actually isn't, right? It's using a common framework, a statistical framework, but it's not a hidden Markov model, nor a hidden summary Markov model, right? It's really just borrowing some of the methods, some of the stats from these methods. Now, all what I gave you here is a case where we would know the number of events, where we would know the parameters, but this is actually something we want to estimate from the data. And the way this goes is, again, sorry, this will be a set of equations that are a bit annoying, but if, again, you want to come back to this, it's written here, also in the paper. But the idea is that when you try to estimate those from the data alone, what you do is that you just assume a starting point for your parameters. And your parameters are that many coefficients, so channels times the number of events that you expect in the data. And in this case, 3 parameters, one for each time distribution for each event, right? And that's your number of parameters. In this case, well, you have a 4 times 3, so it's 12 coefficients for the channels and 3 time distribution, so that's 15 parameters. So what you do is that you first start with an expectation. So usually we don't actually use expectation. We just put everything to 0 and see where things go. But you first use this initial starting points, and you see what the log likelihood of that is, and then you update this previous one. This previous one based on the new probabilities that you computed, right? So the idea is that you start with something, you estimate probabilities for the events, and then you use those probabilities for the events to compute a new set of parameters that better accounts for those probabilities. And you do that on and on and on until you reach some kind of criterion for a convergence, right? This would be some kind of criterion anyway. In the tutorial, it's written what we chose, but this is not very important right here. The only thing that is really important is that we always start with a set of starting points. Then we update this based on the data up to the moment where the likelihood stops to increase at the given level. Now, let's go more concrete, maybe. How do we actually use this HMP method on real data? Well, this is the next section. So this section is, we kind of always assume that you're starting with a physiological time series. So this would usually be EEG, MEG, or even ECOG data, maybe also intracranial data, but I'm not sure how it would work in this case. Or you could also think of MRI, but this is the method I'm presenting today is not yet tailored toward that. So it's really only about EEG and MEG. That's for sure something that works. And what you do is that you usually have some kind of recording, as you would have on your computer, in your acquisition computer. And you would see one line per electrode, and you have triggers in the data, right? Trigger that gives you when stimulus started, and a trigger that gives you the moment of the response. Well, the first thing that we do when we have this data is that we parse the sequence from the stimulus onset to the response, right? We are, as I showed you at the beginning of the HMP method part, we are expecting that there is a sequence between a defined duration at each trial. So in this case, it would be the time between the stimulus onset and the response onset. Once we have that, one thing we do is that we take a PCA. So we just try to transform this 64 channels into a lower dimensionality representation, because we don't want all those 64 to be in the data. Otherwise, it just takes forever to run. But we want to keep the information maximal, so we would take usually 10 PCs or anything. Here, I just represent the topographies from the PCA. It's not super important that you get how this is done. This is basically just to say that we have a new set of virtual channels, a lower dimensionality one, that we then cross-correlate with this pattern that we expect in the data. Now, what we do when we have that is that we try to infer the number of events through a cumulative approach. So these plots are going to be filled as I progress through the slides. This would contain the distributions that we estimated. So remember from the previous slide that we expect some kind of distribution. This would be the coefficients of each event for each principal component. This would be the by-trial probability for each of the events for a different number of trials, for different trials. It's actually real data, by the way, that I'm going to show. And this is the average representation of these coefficients and the timing of the actual event. So let's take a look. What we usually do is that we initiate an empty HMP model without any information on the data. And we start by assuming that there must be an event at just after stimulus, right? So what we do is that we give some distribution that says we can basically be flexible on that, but we usually say it must be around here somewhere. And what the algorithm does, it goes through this expectation maximization step that I showed you earlier. And at some point, it stops increasing in terms of likelihood, so it just stops. If I do that for this data set, that's again real data that I'm going to show you later also in the hands-on part. If I do that, well, this would be an example, right? So this is the time distribution that I estimated for this first event, that is represented like this in the principal component space, not important to be able to read it. And these are the single trial probabilities of this thing happening, right? And you see that we have quite some evidence to say it's happening at this time for this trial. This trial is a bit less certain, so we know it's around here, but we're not sure of where exactly, and so on for all those trials. Now, once we have had this one, we just assume that there is actually one more. And what we do is that we assume that there is a time distribution that there is an event that must be after this one happening somewhere. So again, we initiate it with the very liberal parameters, both in terms of magnitude and in terms of timing. And we see how the expectation maximization converges again. In this case, it will produce this kind of P1-like activity. And then we continue. Again, we assume that there are actually 3 events. We give some starting points, and we end up with this solution, which would be like some kind of N200. And then we continue up to the moment where we reach the reaction time. Well, then the idea is that the sequence ended, so there cannot be an event after this period. That would be the average representation of the reaction time, the average reaction time. And this would be the average representation of the events that we just estimated, right? So we started by assuming that there is one, and we let the algorithm basically decide where to land and how much events to add based on the data that is being fed. And we then get a bi-trial representation for each of those events. You have the blue one, the orange one, the green one, the red, and the purple. And you can then see trial by trial how strong the evidence is based on the data through all these operations that I showed you in that particular trial. Now, this is only one way of doing it. Alternatively, what we can also do with HMP is just assume a number of events, and then in this case, you just fit an I event model. And for example, if I only want 3, I could fit a 3 event model, and then this would look like some subspace of this solution. So, in terms of what do we do with that? Because that's really the product of HMP. The HMP method is working towards estimating the single trial probabilities of the events that were detected in the data. That's really the target of the method. Now, what we can do with that information, well, I'm going to only present you one way of doing things, but then there will be plenty of ways, right? If you have access to that information of where things and what things are happening in time and how likely that is, then the things you can do with that are very, very large. But the way we usually do it, and that's actually a pity, because we just basically look at the maximum of those probabilities per trial. So we look for the first event, where is the maximum probability? For the second event, where is the maximum probability in this trial? And so we end up by having a discrete representation, which is kind of a shame because we lose information, but at least that's a bit simpler to deal with for now. And that means that for this particular trial, well, the first event happened at X samples, the green one at X samples, and so on, right? And then that's the information we extract, and with which I will show you which can work for plenty of aspects. And one of them would be, well, just to see the timing of the components of the events. And that's, for example, a distribution for the event position, where you can look not based on probabilities now, but based on those maximum probabilities points. Where in time did things happen during my reaction time or my saccade time? And you see that the first one always peaked very sharply after stimulus. Second one was a bit later, before 200 milliseconds. Third one was a bit later than 200 milliseconds, and so on. But we can also look at the event duration. And the duration would then be the difference, for example, between green and red on this trial was equal to that many samples or to that many milliseconds. And we can then look at the distribution of those durations. But what usually we don't care about distribution, which I think is a shame. But in this case, we kind of want to know, okay, what is the difference between my participants, or what is the effect of my experimental factor on a given duration? And this would be, for example, a representation where we just average for all trials. We take the difference for all trials. We take the difference between sequential events. So this would be the first interval, this would be the second interval, this would be the third interval, and so on and so on. And we average all those durations, and this would then be, okay, we ask our participant to be fast in one condition, accurate in the other. We just look at the duration of the event, and we look where the maximum effect is located or where the main effect is located. And in this case, we see that participants speed up a bit in every of those intervals, but mainly in this one that is in the middle. So the one that is between the green and the red one. This would be the one that contains most of the variance from our speed accuracy trade-off example here. Now that's only one way of doing things, because what we can also look at is inspecting actual electrophysiological data. And what we can do in this case is, this would be the average ERP for 2 electrodes that are taken here. The condition was just was a stimulus dim or some middle value or bright. And we can then look at this ERP for these 2 electrodes, but by aligning, instead of aligning to the stimulus, like this 0 would be stimulus, instead of aligning to stimulus, we align for each trial's most likely time of the event. And that's basically how you move your representation of this average ERP towards a more correct representation of what is happening at a single trial level. Right? If we take this example, so each of those lines is the average time of our events. And in this case, what we do is, again, we do the same averaging procedure, but instead of averaging from stimulus, we average from the most likely time of the event. And you can see how this is the same Y scale here, right? And this changes the representation of the data quite much, because also we don't, or at least we suffer less from this time jitter, because we're trying to account for it by estimating the moment in time where things actually happen. So if we take a simulation example again, just to make things very clear, this is a single trial I simulated, and you see that again, those have signs inserted at several times. And what you see is that, again, you have a variation in when things in time happen. Those are the topographies that were actually generated. And we just took one of the electrodes that was around here to make this representation. And then we plotted the average ERP. And that's the same conclusion as what we saw earlier, that this is pretty much washed out compared to, for example, the units that we actually simulated. And this doesn't really present any of the peaks, right? You don't really see a peak here, you don't see one here. However, if prior to this averaging, we do align for the moment of the event, in this case, it's easy because it's noiseless data, then we do see that we have the exact same representation as the single trial counterpart, right? So this is quite convincing to show you that we can recover timing and then also average things with respect to when they happen in time. This would just be when we show that simulation is the same as estimated, but again, in this case, it's noiseless data, so it just works like a charm. But usually our EEG data is much noisier than that. I'll come back to that also later. So before moving on to the applications, I want to point out three or four, some would say, of the core assumptions of HMP. So the one that are really important to keep in mind when you apply it on your side. The first one and the fundamental one, and it's the one I started with, also by presenting the model by Anderson and the collaborators, is that the events in the interval that you're considering, for example, reaction time, are sequential, right? So you kind of build on the idea that they are sequential through the math I showed you on the earlier slides. So you have to have this assumption that is true. Otherwise, you would have problems in estimating the events that are underlying. So this would be two simulations. Again, this is noiseless data, just to show you how we break the model by rendering one of the assumptions false. In this case, it's an example where I simulated 4 events again, but this fourth event is not dependent on the other ones, right? It just has its own time distribution, and it doesn't care when this one happened in time, nor when the response was committed. So it's really just independently moving around in the stimulus response interval. In this case, we don't observe it on the HMP solution, right? Because when we have estimated this one is actually not giving us any information on where this one is looking. So it's basically just randomly before, after, or very much after, and we therefore miss this event. So you can imagine this as, okay, I have a stimulus. This is both, I would say, a curse and a benefit. Imagine that you have a mask that is onsetting on the screen all of a sudden, but this is not related to what's actually going on in the brain. Well, then it's possible and probable that you won't see it because those events are not sequential to the one that are occurring prior in the brain. Another way would be, okay, if 2 happens at the same time, that's also a different violation of the sequentiality, because in this case, both are sequential, but they just happen at the same time. Then the algorithm cannot recover it because it cannot assume that things are overlapping. So either it will just separate them, or it will just make some kind of merged representation of both. Then the other assumption is that events are transient, right? We expected in this case a half sine pattern. So what we did was just to, instead of having this half sine, make a full sine wave and either have it phase locked at stimulus onset or not phase locked. But when you see the phase lock case, if you have this half sine that is going on with the same period at all times, with the same phase, then you see it at the average ERP that is completely contaminated by this 10 hertz alpha wave. And you don't see it when it's not phase locked, but that's what we know. But what is interesting is that the yellow event is the one I turn into alpha wave, and you don't see it anymore in the solutions, right? Because it's not transient, and therefore it's not captured by HMP because it doesn't finish in the way we expect it to finish. But this would be one example. Also, in some cases, can be a good thing, some cases can be a bad thing. But in any case, what you have to remember is that we expect events to be transient. The other thing we expect is that events should be repeated across trials. What that means is that, well, if your participants are doing something, for example, looking at stimulus, you expect that it's the same sequence, more or less, that happens at every trial. Otherwise, you would have some problems. These are 2 simulation cases, one where I assume that where I simulated 40% of trials with that green event, and one where I assume 20%. And you see that in the 40% case, we do find it's weaker than the original representation, but it's because it's not there on 60% of the trials, right? So that's also something important to keep in mind. It's not because you have an event that you will necessarily have a correct representation of that event at the trial level. Maybe it's only occurring on some trials. But it's definitely certain is if it's rare, we don't see it, and it's also not contaminating the others in terms of estimation. The final one, I actually added because a lot of people are asking me about that, but this is not a separate assumption, right? The idea is that the duration that you're modeling, for example, reaction time, contains the sequence, but it's actually related to the fact that we expect the events to be repeated across trials, right? So if instead of taking the reaction time, you would take a fixed length epoch, you have two problems. The first one is that on some trials, the sequence will actually end after the epoch size that you chose. And on some trials, it will end much earlier than the epoch size that you chose. So in the case where it ends up earlier, you would have more events happening in this fixed length epoch. For example, I don't know, metacognition or stuff like that. So this will be contaminating the estimation of the other trials. And the trials that are longer than the epoch size that you actually chose, then you will miss some of the events that are happening outside of this window, right? So even though it's theoretically possible to just use a fixed length epoch, this is actually not something we advise, because you're not certain of where things in time are happening, and thus also not what the estimation you do is worth, because you don't have a reference for this sequence. Now, I also list some ancillary assumptions. What I list ancillary is basically assumptions that we can work on easily and relax. And the one that is important is that the events are underlying the signal, right? The events that you have truly in your EEG signal should be equal or shorter than the expected durations of your pattern. Here you have two cases. The first column is when I simulated 25 milliseconds in the data. So in the data there was those 25 milliseconds events. And one case I simulated 100 milliseconds half sign, so very large, in the signal again. So this is what is happening. This is basically the ground truth. There were 25 milliseconds half sign, or there were 100 milliseconds half signs. And these rows are basically showing what happens when I have an expectation on the duration of those half signs. What you can see here is that when I'm simulating 100 milliseconds, but I'm expecting 100 milliseconds, everything goes fine. I find my 3 events that I simulated. And however, when I'm simulating 25 milliseconds half sign, because the underlying the signal is much longer than the one that I'm looking for, I'm missing them. I'm also misaligning in time where I actually generated things. But things get better as you decrease in the 25 millisecond case. The more you decrease, the closer you get to the actual size of the single trial generator, the more correct the solution is. And the good news is that if you have in the data patterns that are longer than the one you are expecting, then it would be fine in most of the cases. It's just that if you look for too small patterns, then you might have duplicates of the same events, because you can fit multiple of your small events into one of those big ones. And this one, I'm not even going to rediscuss it, because the time distribution is a factor we use in the equations, but it's actually not important. The only thing you need to keep in mind is that whatever time distribution family you choose, usually you don't choose any, you would just go with the defaults, but whatever you choose, it shouldn't exclude any likely values. Now, a note on signal-to-noise ratio. I'm going to go quick on this one because it's actually taking quite some time already. So I'm just going to give you a quick overview. This is an example of how I simulated different signal-to-noise ratio. This would be 1/10 of a standard deviation of the noise, right? So you see those plain lines are the actual source signal in this case, and the transparent one are the actual recorded EEG that contains both noise and that activity. And this would be the lowest level. This would be a half standard deviation of noise. That's the amplitude of the actual signal in the electrodes. And this would be if both noise and activations are equal, at least in terms of standard deviation for noise. This would be the ERP you get for those different levels, for 2 electrodes, for 3 or for 5 simulated events. And you see that here it's basically noise, right? You don't see any ERP. Here you start to see that there are some change in the average ERP, but it's still not very clear. And here, this would be 1/1. So this would be the case where you most clearly see things happening at the ERP level. So you can also think a bit of this as the data you record. Does it look more like this when you do the average ERP, or does it look more like this? If it looks like this, you're fine, because we basically find all the solutions that we actually generate in the data. So on the applications, I'm going to try to rush a bit because I don't want to take too much time from the hands-on session. So on the application side, what we did was first to apply this in the paper about the method. on data set collected by Kaplan and collaborators, which is part of this ERP core database, which is a large database for different ERP tasks and therefore also components. And what we did in this case was just to use their P3 active visual oddball task, which is just answer to the letter. And they had to provide an answer both whether it was a rare case or a frequent case. And they were looking for this potential, this one that they call P3, that happens in the brain around 300 milliseconds after the stimulus, only or mainly when it's a rare one. And this is a solution that we have when we fit HMP the way I told you before. And you see that we have 3 components in the frequent case, and we have 4 components in the rare case, right? And this is then what we would call the P3, because we have a very strong positivity at the central level, while this would be more like an N200, and this would probably more be related to the response execution part. And if we look at the average ERP, we have the same as they have, because we basically just took that data that they pre-processed and we just changed the reference. It's not exactly the same. This one is average reference, and this one is reference to some mastoid electrodes. And what we see is that the single trial representation is very interesting, right? Because we don't have this broad representation of the P3. Instead, we have a relatively sharp peak that is happening with timing around, 100 milliseconds or around something like that. Another example is a decision-making task that we just published as a reviewed preprint in eLife. And it's a nice one because you kind of expect 2 things happening in the reaction time. You expect that by increasing contrast, that the time you see the stimulus will be faster as you increase the contrast, but the time you need to decide, which was actually the task of the participant, increased as you increase in contrast, right? The reason for that I let you read in the paper. But the thing is that we expected that both effects should be present in the data. And if we look at the reaction time, when we ask participants to be accurate, the reaction time is clearly increasing with the increase in contrast. But in the speed condition, the reaction time is actually more a linear function rather than this nonlinear one that we expect. And we do see that there is some evidence, a tiny bit, for the law where we predict a decrease. So what we did was just to analyze the EEG data using HMP. And what we see is this. So this would be the intervals between each of those events. The average one, so per trial, per participant, and we average all that for each contrast level. So this is 1 point. And for each trade-off condition, I'm not going to go too much into detail because we don't have time. But what we see is that we have 2 early periods where the duration of the stages are actually decreasing when you increase in contrast, while later portions of the reaction time are actually increasing when you increase in contrast, right? So we are able to split the intervals into an encoding and a decision part, and this then shows up like this based on HMP. So we can split the reaction times to show different periods of information processing based on those events. Another thing we can do, I showed you earlier some ERPs that we can have if we just look at the time of the event instead of looking at the stimulus-centered version. What we can also do, and we did it in this paper that I'm going to give the link at the end, is that we can take a topography. This topography is basically just weights of the electrodes. And we can, again, do the dot product of that, of those weights, those coefficients, with the actual bitrial time series. That would mean that we take one sample here, and multiply the electrodes with each of their coefficients, and then make the sum of that, and this gives a 1D representation, which gives you how much does the data look like this topography at a given time. And you would see, for example, that in this case, this particular topography that comes from HMP is peaking around 500 milliseconds, which will, of course, also correspond to the moment in time where the probabilities of HMP tells us that it's most likely. What we can do then is have a single trial representation of that. Those are surface plots. I'm not going to go into details, but this is basically aligned on the timing of the event, and we can then look at how did the buildup of this particular topography, for example, happen. And in this case, we see that the last one has this increasing ramp that in the paper we also interpret as evidence that this is a decision component. And this we interpret as a motor component, also because when we look at these average topographies, but we split them for right and left, not for right and left responses, because in this case, I also always answered with the right hand. But if we look at the difference between left and right electrodes, so if we subtract the right electrodes to the left electrodes, what we see is that this component has a strong negativity over the motor cortex, right? Suggesting that this one is actually capturing the moment in time where you start executing a response, while the later one is more related to the decisional aspects, also shown by this chronometry thing that I showed earlier. So at a side note, we'll come back to that in the hands-on session, but there are two versions of that paper. The first one we submitted, it's available here. We used a 50 milliseconds pattern, right? Because that's the standard way we usually did it. But the reviewers, and you can also look at the reviews here on eLive, kind of missed that there was some motor component going on. We're pointing out that maybe this is not a complete solution. So what we did was to just decrease the width of the pattern to try to be more precise on the events we're locating. And this is then the new solution that I showed you, where we also have this motor execution event, and where we have this early, very early visual potential that's happening right after signal sounds. Okay, time to wrap up before moving to the hands-on part. So the perks of HMP, if and only if all assumptions are correct, we can access a single trial time of information processing components in the EEG. And this gives you plenty of opportunities in the sense that you can decompose any duration, saccades, keystrokes, movement time, reaction time into relevant subintervals, relevant in the sense of task-relevant subintervals. Then we can describe task and condition based on underlying sequence of components and describe these components in time and space, as we did in the applications. And we can time lock follow-up analysis on specific events, right? Imagine you want to do source reconstructions or time frequency. Well, my bet is that this is going to be helped a lot by knowing when in time things actually happened. And we can also use task-derived spatial filter as shown in just the previous slide. And some advices. I'm also going to go back again to those in the hands-on part. But first, you should also keep in mind that this is work in progress. The model is work in progress. At this stage, what we have seen is the following. It is better to apply that method when you have strong hypotheses, right? Because if you're just wondering what would happen, then you're also at risk of making a hypothesis after results are known, so harking. So that's something you should avoid. You should have something that's really constraining your interpretation in order to not start to go crazy and give crazy interpretations, because the model will fail, and you can see it also sometimes hallucinates things. I guess it makes it kind of an AI. And another advice would be to start with relatively short intervals, right? I have a lot of people who ask me, can I apply this with 10 seconds EEG? This is not a good idea. Not necessarily because the method wouldn't work, because in theory it would work. However, both computation-wise, it's going to take a lot of time. And also in terms of assumption, I'm not sure that when you ask your participant to do something for 10 seconds, they will actually do the same sequence all over. Right? So there might be up some mixing among participants, within participants, that makes it this assumption is just not able to hold in this kind of data. Another recommendation is to start exploring with low precision or downsample data because it can be quite long. And if you are inferring events from the data, that's an important one. You should always keep your trials, amount of trials as high as possible. That's why it's mostly recommended to apply that model to a group level rather to a participant level, because you can run into cases where it's actually noise that is driving the number of events instead of actually the data. And I'm of course often asked, what is the recommendation in terms of number of trials? Well, I have not really. It really depends on signal-to-noise ratio of the data. But in general, the more, the better. Also important, don't waste too much information at the pre-processing step. I'm going to show you later, but we have an HMP pre-processing pipeline to avoid just this habit that we have when we also start EEG to just try to have the cleanest signal possible. But this also is about the ICA, right? I usually only remove blinks, if ever. And also at the PCA step that we saw, we shouldn't remove too much of the information. We should keep it as maximal as possible. And this is a list of resources, but you can access that later. And I want to thank the contributors of the GitHub. And if you want to contribute, you're also more than welcome. We are very welcoming new collaborations and new contributors. So if you have some ideas that are not implemented, and if you have a bug report to do, please do so on the GitHub. And that's it. Here are the references you can also find in the PDF on the GitHub file.